Okay, physics students, today we are going to begin our unit on light, and due to the nature of this year, we're not going to be able to get to everything that we ever wanted to get to about this, but we will talk about the nature of light, and we will be talking about reflection in this unit. So, the first thing we want to talk about is just what are the characteristics of light, and I think most of you have some idea of what light is. You can see light coming from the sun. You can see light coming from a light bulb. The truth is, though, that is only what we call visible light. And visible light is a very, very tiny fraction of all the light that exists in the universe. Light waves are electromagnetic waves. And the light spectrum, like I said, it includes much, much more than what we can see. So this is a short little video here of the electromagnetic spectrum.
Electromagnetic spectrum, an immense scale we use to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape, and it's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen, and there's no way to confuse hydrogen in the spectrum with any other element.
Okay, so that again is one of the useful ways that we use light in identifying what different types of elements we have. People say, well, how do we know what kind of gas is burning in a star? And we can use a diffraction grating and look at a star, and we can see light split into very specific wavelengths, and we can recognize what elements are being heated there. We use the visible spectrum, obviously, to look at the sun, but this is what we see when we do that. Looks like the regular sun. If you look through it with look through a very powerful telescope with a filter on it, obviously don't ever look at the sun with a regular telescope, but when you put a very strong filter on it, you can actually see sunspots, which are pretty cool. But if we look at it with an X-ray telescope, this is what you see. Now that you have to add colors corresponding to the different electromagnetic wavelengths in the X-ray spectrum, but this is what you see, and it's obviously much more stuff that's going on than what we ever see. This is an example. This is sort of an artist's rendition, a little bit of a black hole and a galaxy, but this is an X-ray jet coming from either end of the black hole at the center of the galaxy. This is what we see in the visible spectrum. Again, we see these massive clouds of dust, very, very dense, denser than anything you can imagine here. But when we look at it with infrared, we can see through all of that. And that's, again, just a very powerful tool. And it's because of this use of infrared technology that scientists were actually able to use telescopes to look all the way to the center of our galaxy. So these are just some different examples of gamma rays, or I'm sorry, the electromagnetic spectrum and the different types of electromagnetic waves we have. We have gamma rays, which are the highest energy rays. Look at their frequencies here, 10 to the 21st hertz. You're talking about wavelengths on the order of 10 to the minus 13th meters. That's like, what, 10,000th, 1/10,000th of a nanometer. You have X-rays, which are like 1/10 of a nanometer, ultraviolet, which are about 10 nanometers, visible spectrum. Now we're into the 10 millionths. Here we're into the 100,000ths. And then look at radio waves, 100-meter long radio waves, 1-meter long TV waves. So very long, or I should say very diverse lengths here on these. And then, of course, notice that these are all light waves that travel at the speed of light. And so if your wavelength increases, your frequency has to really decrease. So we're talking about 1,000,000 hertz here. And down here, like we're talking, what is that, 1,000 billion billion? So, all right, moving on. So what does an electromagnetic wave look like? Well, electromagnetic waves are transverse waves, but they have two parts, and those two parts are at 90 degrees to one another. You have the electric portion, and you have the magnetic portion. And here you can see the magnetic portion going up and down. That's the blue. Here you've got the red. That's the electric field, but they work in concert with one another, and they're traveling in this direction. All right, electromagnetic waves all move at the speed of light. Speed of light is known as c, 2.99, this blah, 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 times 10 to the 10 to the 8th. We just round it to 3 times 10 to the 8th whenever we do it. 186,000 miles per second. Again, incomprehensible really to think about how fast that is. Our wave equation for light, C equals F lambda, same wave equation we've been using. It's just that now instead of V, which could be any wave speed, because it's light, it has to have this speed here. So again, we use 3 times 10 to the 8th. And we're going to skip that. All right, electromagnetic waves do not require a medium. They can travel through different media, but those media actually hinder the movement of the electromagnetic wave. So they travel the fastest through what we call quote unquote empty space, even though, again, we watched a video a long time ago saying space really isn't that empty. And light intensity is another thing that follows the inverse square law, just like sound intensity did, just like the strength of a magnetic field, just like the strength of an electric field, just like the strength of a gravitational field. As you get farther and farther away from a source, the less and less intense it becomes, and it becomes less intense as the inverse of the square of the distance changes. So here we have one radius away, and you've got all the light going through this particular square, right? So you double the radius. Now the area that takes up is 4 times as much. So now each square gets 1/4 the intensity that you had here. If we triple that radius, now we've got 9 times as much surface area that light had, that same light that was going through here has to all spread out and go through here. And again, you can kind of picture sound waves doing the same thing. You can picture gravitational waves, so to speak, doing the same thing here. Everything spreads out so much more as you go out. And we're talking about, the equation of the surface area of a sphere. All right, and we're going to stop there for today. We will talk about flat mirrors on Thursday.